crashed. So what should I do?
Just wear it.
Yeah, just wear that, and there's a laser pointer in there.
Is the laser pointer where? There.
Central button.
Just the middle button.
But this will not advance my
Not
slides.
advance your slides. If
Right.
you want, if you prefer the old-fashioned stick, then a stick.
Yeah, that way I can hit people too. When does the recording start?
Well, it just started.
It started. Okay. Okay.
Give it a few minutes.
Yeah. That's the
So yeah, when did you come up with Gravitar?
2001.
Okay, so this music is 2 years after that.
Yeah. Okay. So
You get to-
they say that imitation is the highest form of flattery, but I'm not sure if it's,
Yeah.
that applies.
Okay, I think we can get started. I don't see people want to approach. Delighted to have Emil Mottola from Los Alamos. I've known Emil for 10 years that I was there. It was great interacting with him. And he'll tell us about the quantum mechanical aspects of things that we've been talking about for 4 weeks now.
Well, thank you, Sanjay, for the invitation, and to the other organizers. So I see them pushed as the very last talk, so hopefully this will be, some sort of ending, not necessarily the least, but I hope to intrigue you with some ideas anyway. I've been sitting here all week listening to neutron star physics and binary mergers, and basically I'm trying to see if some of the ideas that I've been thinking about from the much more theoretical side could actually be tested, and that's where we want to go. I won't be able to give you specific predictions in that sense, but I want to at least get to that before I conclude, and leave it open for discussion of whether or not these ideas can be tested. So I don't know exactly how much folks in this crowd have thought about or heard about all of the controversies associated with black holes, or these ideas before, but I will review that a little bit, and please tell me if I'm boring you with all that stuff. But of course what I'd like to get to, so I'll give you a background and then talk about quantum mechanical aspects of black holes. These things you've may have seen discussed in the popular literature as well as controversies out there. And I'll describe to you the physics that I think needs to be included to resolve these problems, and our proposal for what might be quite a different interior object, not a black hole from the classical GR textbook point of view, although from most outward aspects from astrophysics point of view, it will be essentially a black hole mimicker. We call it a gravitational vacuum condensate star, or Gravastar, and then we'd like to talk about the observational consequences. So I'll go very quickly through this because I'm sure you guys all know about this. But in order to introduce the subject, you first have to talk about classical black holes, and that's of course what you're mostly concerned with in this workshop. Most people don't think of quantum effects. Well, I should say the fact that there are neutron stars is certainly a quantum effect, right? I mean, and when it was first proposed by Kruskal-Szekeres, it seemed pretty exotic. But now we have workshops, talking about observations and actually what's happening in neutron stars and and the dynamics. So it's a macroscopic quantum effect. To have a neutron star held up by its degeneracy pressure, it certainly was a wild idea when it was first suggested. Now it's a commonplace. So quantum effects can play a role in astrophysical objects and large objects. And so that's sort of the first hurdle you need to get over. But the classical picture, of course, there's no h-bar whatsoever. If you just write down the Schwarzschild metric as the simplest case, everyone agrees that something has to give at the origin, where you have infinite tidal forces, breakdown of general relativity, usually start talking about quantum effects and wave your hands, although no one quite knows what's going on. The important thing I'm going to emphasize is that even the event horizon, which is of course a large object, macroscopic, kilometer scale, is where the problems really first start. And if you don't do something there, you may already be in trouble from the point of view of quantum mechanics. So, okay, that's just saying things that you know. As you also know, the standard picture in textbooks is that classical matter reaches the horizon in finite proper time, so the local Riemann field tensor strength is finite and moderate, nothing wild about it. And one can write down coordinates due to Kruskal and Szekeres in 1960, which basically penetrate the horizon and analytically continue the Schwarzschild geometry inside. And in that way, you can go all the way down to the origin without seeing a problem. There's certainly a singularity at the origin, but this is the standard way of going through the horizon and saying that nothing special is going on there. The thing to emphasize is that this involves a complex continuation of coordinates, and nobody told you that you could do that. It's just was assumed. So the usual Penrose-Carter diagram you see in books is that, for example, the Schwarzschild geometry, the exterior universe is this right-hand quadrangle, and an infalling particle goes through. This is the future horizon, and that's just the null surface where t is x and those Kruskal coordinates. There's a singularity at r equals 0. You see this Penrose diagram is at 40, light rays are at 45 degrees. So you see just pictorially, once you're inside the horizon, you have no choice. If you're future time directed, you're going to hit the singularity. So it shows the causal structure very clearly. And if you analytically continue the entire geometry globally, assume it's static and Schwarzschild everywhere, then you get this global Penrose-Carter diagram, which has a second flat region out there, and the time reverse, because Einstein's equations are time reversible. You have a white hole in the past, and of course no one sees those things, although they're just as good a solution of Einstein's equations as a black hole. And we usually say, well, this was just created by some collapsing object, and we only look at some half of the diagram here. But Einstein's equations don't know the difference.
So, can I ask, all this
Sure.
stuff I hear about firewalls is because...
We're about to get there.
Okay.
Ask your question. Go ahead.
No,
Or you
we
want
don't have to worry about this because we're still in classical.
It was all classical, yeah.
Okay.
Yeah, let's skip it. Okay. So what's less well known, but also very, marvelous subject, if you go into it, is the classical general relativity of rotating objects. So the Schwarzschild, of course, is non-rotating, zero angular momentum. But once you put in rotation, and actually even a little bit of rotation, you change the whole global picture completely. The Kerr solution can also be analytically continued. It has, in fact, an infinite set of universes, wormholes, closed time-like curves in some regions, so you can go back in time and say hello to your great-grandparents. So, you can take any point of view you like on this, but I would say that these interiors are rather unphysical from the point of view of ordinary physics anyway. And almost everyone believes that something else has to happen before you get into these serious problems with causality, for example. And notice that everything here is happening on the scale of, the object. This is not something that's Planck scale, because there's no Planck physics in this. This is just classical physics. So these issues come at macroscopic scales, the scales of the black hole itself. Now, the other interesting and important fact about classical black holes in general relativity is the no-hair theorem, namely that all classical black holes specified by their mass, angular momentum, and electric charge. And this is very important also for astrophysics, because if you assume the standard picture, then Kerr black holes have no hair, which means all their higher multiples are completely determined by M and J. So whereas any ordinary object, in electrodynamics, if you have a charge distribution, it can have any number of multiples. You have a multiple expansion. There's no reason why the multiples have to be related to each other. It depends on the interior of the charge distribution. But in GR, there are no solutions to the equations, the vacuum equations, Einstein's equations, except these, which have very simple properties in which all the multiples are determined. And so therefore, if you have rotating black holes in the universe, you know all the multiple moments, and you know all of the orbits exactly without, in principle, having to calculate the interior distribution. So that's different from a neutron star, of course, because the neutron star exterior geometry is determined by the interior equation of state. And here, basically, it's universal in the classical vacuum equations. The other interesting thing, which was...
Not only universal, but also extremely difficult or impossible to duplicate with the method distribution.
Well, that's my point, yes. It's, that's what I basically was implying by talking about these very, very funny interiors. There's, I think, to this date, no successful realistic matching of an interior non-singular geometry to the exterior black hole. That was a long-standing problem. So there's something you should worry about. I mean, there are some issues even at the classical level, even before I put H-bar in, which is what I'm going to do in the next slide. But the interesting fact, very important in this whole subject, is the existence of something called the irreducible mass, which is given here by some quadratic formula in terms of the angular momentum and electric charge. So for most purposes, we can forget about electric charge. We don't think we have macroscopic electrically charged objects. The electric field would short them out very quickly. But forget about electric charge. You have angular momentum and mass. And then there's this quantity that Christodoulou showed is always increasing if you make apparently reasonable assumptions about classical matter falling on, positive energy. You will get that this quantity always has to increase. So that's a classical result. There's no H-bar at all in there. Next, we start thinking about quantum mechanics. So the first thing to say is that, what is entropy, right? I mean, all this discussion goes back, I guess, to Wheeler in the 50s at Princeton, asking his students, what happens if you throw a warm cup of tea into a black hole? It had entropy, and now the entropy's gone. So have we violated the second law of thermodynamics? So the first thing to say is that usually a classical solution of any equations, I don't care how complicated they are, you would normally not call the Coulomb potential to have any entropy, right? It's just a classical solution. If I concentrate all the matter, all the charge at a point, then whatever entropy is associated with that matter distribution does not show up in the classical solution. But the problem, of course, is that for a black hole, you have this causal structure and stuff seems to disappear on a macroscopic scale. So because I have this irreducible mass, which is always positive and growing due to classical perturbations, Bekenstein basically suggested back in the 70s that maybe this is where the entropy goes, that there is some formula relating the entropy of the interior to the area. Now, it's usually not emphasized, but if you think about it for a few minutes, you realize that this has the wrong units, right? The area is units of length squared. The entropy is units of Boltzmann units. Boltzmann's constant is dimensionless. So you've got to have a length scale somewhere. But there is no length scale in classical general relativity. The only length scale you can think of that might be at all related here is the one that's given to you by the fundamental constants of Planck's constant, Newton's constant, and the speed of light, and that's the Planck scale, which is of course a very small number, 10 to the minus 33 centimeters. But if I do divide the area by that scale, then I will get something that is units of entropy, and it will be a very large entropy, because this is a very small number. And that was not necessarily a very persuasive argument, but very soon after that, within a year or so, Hawking came up with this famous formula arguing that, much to the surprise of most people at the time, that a black hole, instead of just absorbing stuff, could actually re-radiate it at a thermal distribution at the famous Hawking temperature, and here I've kept all the fundamental constants in. So that suggests a very deep connection between thermodynamics, quantum mechanics, and relativity, and it's basically summed up in the black hole formulas, which one important part of which is just the first law of thermodynamics, that dE, which is dm, is the temperature times the entropy, and this actually fixes the constant, which I should use the pointer, I guess. This actually fixes the constant, which Bekenstein had said was order of 1, actually fixes it to be 1/4 if this formula of conservation of energy in the first law is supposed to hold. Now, we're going to discuss what the problems this leads to, but the one important thing I want you to recognize is that the Christodoulou formula was a classical formula, had no h-bar. The mass has no h-bar. But what's happened here is that I've essentially multiplied and divided by h-bar. So the temperature is proportional to h-bar, and the entropy is proportional to 1 over h-bar through the Planck's length. So, you know, this is for the undergraduates when you're teaching undergraduate physics. It's not always true that you get a quantum formula by multiplying and dividing by a classical formula by h-bar. It doesn't make it quantum. So it's basically still a classical formula. You've just laid it with interpretation that's quantum mechanical. So what are the problems? The problems are many, and you know, we could easily get bogged down in this. People usually do. There are many problems. So one is that this entropy is huge. It's about a factor of 10 to the 19, and I'll also show you. Compared to progenitors, which you guys are all experts at, it's much, much larger than many orders of magnitude larger than any progenitor. It's proportional to the area, which is also strange because entropy, as we're usually taught, is an extensive quantity proportional to the volume. So this leads to other issues. If you propagate these so-called Hawking quanta backwards from where they originated, they're coming out with a very low temperature. You see, if m is large, this is a very small temperature. But if you propagate them all the way back, since they had to climb out of a steep gravitational potential, they were redshifted. So if you propagate them back to their blue shifted form, they actually go to infinity. They produce frequencies of the radiation near the horizon that are actually as large as you like, infinite if you go right up to the horizon. From the point of view of thermodynamics, this is all very strange because we have a classical limit where h bar goes to 0, or if you wish, m goes to infinity. The temperature becomes very small, goes to 0, but the entropy, according to this formula, becomes infinite, becomes large. So it's a bit strange from the point of view of quantum low temperature physics that you can have a cold system with infinite entropy. Where are all these states that are excited at 0 temperature, usually at 0 temperature in the vacuum, right? The other issues related is that the energy is proportional to the temperature to the 1 minus 1. It's inversely proportional, and so dE dt is negative, which means you have a system with negative heat capacity. So the more you put in, the colder it gets, which also is a problem from the point of view of fluctuations, because dE dt, as you also learn in first year thermodynamics, is proportional to the root mean square energy of fluctuations of the system. So it means you have large energy fluctuations on short time scales at a very cold system. So this is rather peculiar, and in fact would lead you to think the system is unstable, because if this thing is negative, then you really shouldn't be applying equilibrium thermodynamics. The problems go on. Where's all this information? You have this entropy. Where did it come from? What are the states that you're supposed to average over, sum over, trace over, in order to get the entropy according to Boltzmann's formula? So, this led people like Hawking to talk about unitarity being violated, and led to controversy that I guess is still going on. So here's a simple argument for you guys, which I like, because it is just a back of the envelope calculation. One slide, you can basically estimate what the entropy should be from standard thermodynamics. The energy is the volume times T to the fourth. The entropy is the volume times T cubed. Eliminate the temperature. The entropy goes like this. If the volume is R cubed, it goes like the size times the energy to the 3/4 power. If the energy is just m, and I'm talking about a gravitationally bound object, it's also m, you just plug it in, and the entropy is m to the 3/2. If I keep track of all the h bars and c's, it's m over m Planck to the 3/2. And this is correct, okay? This is an upper bound for a relativistic star. If you look at Zeldovich's book, this is the entropy of a massive star in the 50 to 100 solar mass range, which is dominated by its radiation pressure. So this is actually, these are actually the correct formulas, and you get the right estimate. The sun, of course, has a lower entropy because it's not relativistic. It's dominated by just ordinary perfect gas equation of state, non-relativistic. But if you make the mass of the order of 50 to 100, you will get radiation pressure going up, and you'll get an entropy like this. The important point is that this is nowhere near the Bekenstein-Hawking entropy, which goes like m squared. Remember, it's the area, and the radius is this, so it goes like m squared. And here's where here's your discrepant factor. You're off by m over m Planck to the 1/2. So for a solar mass, this is a factor of 10 to the 19. Okay, so you have to understand, if you believe this scenarios, that somehow you could get a factor of 10 to the 19 in entropy, or e to the 10 to the 19 more states, microscopic states in the system, in order to get from a standard progenitor to something which is Bekenstein-Hawking-like. Okay, I'll skip this. This is, this is for fun, but these things have still been discussed. So back in 2013, you mentioned firewalls, so we can talk about that if you like. So I'm going to describe the stuff that I talked about years ago, and what the update on it is. But we described some kind of phase transition or boundary happening at the horizon. I hope I'm convincing you with these issues that something has to happen at macroscopic scales. It's not the Planck scale that's really where the problems happen. They happen as soon as you have this horizon and quantum effects building up in that region. So recently, last couple of years, there's this stuff that's been talked about by Joe Polchinski and collaborators at Santa Barbara. They called it firewall, and they basically argued that if you just assume standard things, Hawking radiation coming out, a pure state, quantum mechanics is not violated, unitarity, entropy has to be conserved, information is carried out by the radiation in some standard low energy effective field theory, and you assume that nothing happens at the horizon, you get to basically a contradiction with quantum mechanics, that something, you end up with states that are more entangled or cloned, as they say in quantum information theory, that just can't be, just can't happen by standard unitary evolution. So you end up with a contradiction. So their paper is basically a proof by contradiction that all three of these things can't be true. And then they say, well, what should we throw out? We don't want to throw out Hawking effect. We don't want to throw out effective field theory or quantum mechanics. So something should happen at the horizon. And I invite you to go to this website and see people arguing about this. And then last year, Steve Giddings wrote an article in Physics Today, which we actually have a letter responding to. You can read that stuff. So what is fun here is that he actually wants to have a massive remnant inside, which then somehow later on, so it's a standard black hole on the outside for a long time, and then eventually at the so-called page time, when it's evaporated almost half away, this remnant which forms then jumps out somehow faster than the speed of light and violates causality. So that's a cartoon picture, and Hawking has now said in a January that he's now not sure if there are black holes, although you can make sense of that paper. I'd be happy to have you explain it to me. So now let's switch. So do you want to ask about firewalls now, or should I? Okay, I'll keep going. So I'm going to have to go through this fast because I don't want to, I mean, this is the physics, okay? So this is what I've spent most of my time concentrating on, and basically trying to understand what of known physics could possibly interfere with the standard interpretation before we start inventing all kinds of new stuff, extra dimensions of strings, or new quantum gravity models. Is there anything within the standard model that we already know about that could come to our aid here? So the approach that I've basically been following over these years is to really keep track of what the effective field theory should be in gravity, and what are the terms that I need to take into account that might offer significant corrections to Einstein's equations and might lead me to some way out of all this paradoxes. So I won't have time to go through this, but the basic idea is said here in a few bullets, is that you need to take into account what are called quantum anomalies, which are when say the stress tensor of matter is traceless, like for photons, you would normally say that should be true also at the quantum mechanical level. It turns out you can't maintain that at the quantum mechanical level. The conformal symmetry of for example, just Maxwell's theory is broken, and it leads to something called a quantum anomaly. And there's a long story here of anomalies in field theory and what kind of role they've played in our understanding of theories like QCD. I won't go into all that.
But are you still doing semi-classical gravity then?
This, for the moment, is still semi-classical. Yeah. So I haven't. This is conservative in some sense. I'm just trying to understand what kinds of effects. So here's your answer to that question. So if we were trying to do in a modern way construct an effective field theory, in a sense, what Einstein did was an effective field theory. He wrote down the simplest theory, which respects the principle of equivalence, which has no more than two derivatives of the metric. And that the effective field theory you get from that point of view is nothing else but the Einstein's equations, with the only freedom is to introduce a cosmological term. However, we know a little bit more, than in 1916. We know there are quantum effects. We know that the stress tensor of quantum matter does have this anomalous contribution. This was understood in the 70s. And so even if you have start out with conformal matter, which is massless, you can show that the trace of the expectation value of the energy momentum tensor in semi-classical gravity cannot be zero in curved space, and these coefficients have been calculated, b, b prime, b double prime. C squared these are curvature invariants. This is the Weyl tensor squared. R is the scalar curvature. E is some other invariant, Gauss-Bonnet invariant, never mind. The point is that this is all known, and this leads to an effective action. There it is. I'm not going to dwell on it. You can write it down. And the important point is that if you write it in a local form, it's totally covariant, so I haven't violated any principle. General covariance, one-loop physics, that's all that's gone into this. But you can write this in terms of a certain scalar field to make this ugly non-local thing into a local form, and then you can actually compute with this thing. Okay, so this was an elaboration, if you wish, of earlier work, and our point has been that this term should be added to Einstein's theory in order to have the proper low-energy theory of effective gravity. And then you ask, what does this thing do? Does it ever become important? Okay, so one thing you can do is once you have an action, you can vary it, you can calculate the energy momentum tensor, and this phi is now a new scalar degree of freedom in low energy gravity, which, if you trace it back where it came from, it contains information about the vacuum state. It came from quantum effects. So in a sense, it's basically encoding information about Casimir effect and the quantum vacuum, and this is a way of calculating in a very compact way compared to what was done before what the quantum effects might be in black hole space-times, and we can show that it is in general important near horizons. Why is it important? Well, I'll skip this for lack of time. Here's just an analytic solution of the equations. You can write down what the phi is, okay? And the important thing is that it tells you that generically something is going to happen on the horizon unless you tune some integration constants to 0. If you tune those to 0, something else might happen at infinity because things are growing. You see, this is just an analytic solution of the equations, which allows you to examine what's happening both at infinity and at the horizon for all fields all at once in terms of a few integration constants. So basically there's an what you learn from this is there's an obstruction to finiteness at the horizon versus fall off at infinity. So if the vacuum is basically standard at infinity, it's going to produce some interesting effects on the horizon. So here's a solution, particular one of those integration constants, which becomes logarithmically big on the horizon. If you take the derivatives that you need to take in order to form the stress tensor, you find that it blows up on the horizon. It becomes as large as you want. So, sometimes people are troubled by this because, well, how can this be? Well, the point is that it's a perfectly coordinate invariant description. This is a scalar field, and it's basically telling you that when the killing vector of the Schwarzschild geometry, say, turns from time-like, it's static, to null at the horizon, this phi knows about that, and that's a perfectly coordinate invariant scalar quantity. It's just not local. It depends on the whole history of the black hole. So it gives a perfectly good geometric meaning to things becoming large on the horizon, as we were just talking before I came in here. If nothing else, this is a good way of approximating the quantum vacuum polarization. This curve shows what our semi-classical calculation in terms of the phi field does. These were numerical calculations done by these people back in the 90s, and you see it fits pretty well. So it's basically a good approximation near the horizon to what the vacuum polarization effects are. So if you can have large vacuum polarization effects near the horizon, this was shown way back by Bulwer. Where is Dave Bulwer, by the way? Is he used to be the chair here, right? Is he retired or? He retired? Okay. He's still okay. He doesn't come in. Yeah. So he did some of this work way back.
Did you check if the solution is stable, unlike the classical solution?
So this is not a solution yet. This is just fixed background Schwarzschild, and then calculate the vacuum polarization on that background without resolving the equations. That's a background.
Spherical symmetry before obtaining the solutions, or do you?
Yeah, no, yeah. So yeah. Let's be very clear. This is just take a Schwarzschild fixed geometry, fix once and for all. That is the solution. Okay. Then solve for this classical field and stress tensor on it to see if it can ever become large enough. If it's always small, then there's no reason to do anything more than that. It's just negligible. What we're showing is, without resolving the equations, without doing dynamical back reaction, that the stress tensor, due to this vacuum polarization, can become large on the horizon.
So you're just studying the properties?
Just studying the properties of it, yeah. So, yeah, sorry, I have to do some of this background, otherwise, it's just not even going to be able to get to the point. So that may be surprising, but I think it's already contained in some earlier work going back to the 70s that Bullard did, in fact. So if you can have these large stress tensors near the horizon, okay, now we want to jump and do something that's basically dynamical, or at least go beyond the semi-classical approximation a little bit. So the first thing I'm trying to convince you of is that there can be large effects on the horizon. Gravitational effects can become strong. Well, if you have attractive interactions and they become strong, from general principles, quantum mechanics, right, you expect something to happen. You expect some sort of condensation phenomenon. And quantum correlations, which haven't been computed in any great detail, can also become large. So this means you're not going to anymore be able to approximate Einstein's equation by just the expectation value of t, but you have quantum correlations which are certainly not taken into account in Einstein's equations. So this was our speculation. I'm just leading you through some of the ideas here, that this could lead to a quantum phase transition, something like a Bose-Einstein phase transition near the phase boundary, which is described on the horizon scale. And so we basically made a model. This is the model. So that would skip Bose-Einstein condensation. This is the model. And if you just now try to imagine what kind of a state you're going to end up with if you have strong interactions and some sort of scalar order parameter, and you saw in the anomaly you will get a scalar order parameter. Well, you know from other contexts like inflation that if you have a potential function of a scalar order parameter, it's going to lead to a equation of state in which p is equal to minus rho. P is equal to minus rho is actually what you want for many different reasons. It is the dark energy equation of state, and from Gibbs relation, it is a state of zero entropy. So for example, if I have no chemical potential, the Gibbs relation is this, and p equals minus rho just tells me I have zero energy density. In other words, it's a quantum state. It's a vacuum state. It has no entropy. It's the logarithm of the single macroscopic state is 1. So the logarithm of 1 is 0. So that means that the entropy issues are going to be quite different in this kind of configuration. Secondly, the collapse issues are going to be quite different, because if I have this p equals minus rho in the interior, then I violate the strong energy condition, and most of what you know or think you know about black holes is based on the fact that ordinary matter obeys the strong energy condition. Rho plus 3p is positive, and that's what leads to the focusing of geodesics and the ultimate collapse to a singularity. You can't avoid it in Einstein's equations if the equation of state of the matter obeys this condition. But you see, if p is equal to minus rho with rho negative, you violate this condition. So exactly the same reason why cosmological dark energy leads to an accelerating expansion. It's sometimes called a repulsive-like term. It's exactly the same physics leads to repulsion in the interior with this equation of state and prevents a singularity from forming. So that was the basic idea, that, and others have had some version of this in the past, that a phase transition in which the vacuum energy changes due to the compression of the vacuum state near the horizon, as we saw there are some big vacuum effects there, that could lead to an object in which the interior is vacuum-like, de Sitter-like, prevents any further gravitational collapse, and basically the only new assumption you need here from the ordinary semi-classical framework is that the energy of the squeezed vacuum can change. Okay, I have to allow, it cannot be a cosmological constant. If it is, it's constant forever at all times and all places. but I need the vacuum energy to change, and we can discuss how that might happen. But that's basically the assumption. I'm just alerting you. If you make that assumption and just do the usual semi-classical things, then you're led to the kind of picture in which you rewrite the Einstein equations. Remember, there were two functions, I think, on one of those previous slides. For f is the time function and h is the spatial function. So you just write down the Einstein equations in static spherical symmetry. H is just 1 minus 2 gm of r over r. Basically, if you assume that you have a perfect fluid in which p is equal to minus rho inside, p is equal to rho equals 0 outside, and then you have some transition layer, which in that time, at 2001, we assumed was a p equals plus rho, maximally hard equation of state for various reasons. It doesn't have to be this. If you assume this kind of picture, then you will get an object that is static, and from all their attempts to look at it, it looks to be stable. And that's what we call this gravitational vacuum condensate star. That was this model proposed back in 2001. And what I'm now doing is taking this much more sophisticated microscopic theory coming from the trace anomaly that I showed you to actually do this matching. Because, of course, the complaint was, okay, you can do this, that's nice, but what creates this equation of state on the boundary? And now I think we can show that the trace anomaly terms do exactly that. So this is just what the solution, just going through the steps. I won't bother you with it. The point is that you don't have a horizon anymore. So this function f of r, which where's the eraser?
It's on the floor there.
Ah. So I should have had a picture of that. If you have this function f of r, which for Schwarzschild geometry is 1 minus 2m over r, and would go through 0 at the horizon, basically in the de Sitter phase, it's 1 minus h squared r squared, where h is the de Sitter constant, and the matching just does this. So the two solutions match onto each other continuously. The first derivative can have a jump or not, depending on what you assume about the boundary layer. And this layer is very thin. So this is the Schwarzschild radius. And this region is very thin. It's of order, actually, this geometric mean of the Schwarzschild radius and the Planck length. So if this is kilometers, this is 10 to the minus 13 centimeters. Lo and behold, this thing is a nuclear scale. It's about a Fermi. So it's small compared to the Schwarzschild radius, very thin for astrophysical purposes, but very large compared to any quantum gravity scale. Usually you consider Planck scale as the quantum gravity scale. So this function never vanishes, and there's no event horizon, therefore. There's no event horizon. You can also estimate the entropy by just standard thermodynamics, by integrating through this boundary, and you find, not surprisingly, the entropy goes like m to the 3/2. Just it has to because of my scaling argument before. What happens is that this region, this is the length scale L, which is very small, so that's where the small factor comes in. You get the Bekenstein-Hawking formula, but multiplied by L, which has this square root of m in it, so it just reduces it. It reduces the entropy. There's no entropy in the interior because it's basically the de Sitter vacuum, and the entropy is all coming from the shell, which is now of order m to the 3/2. So you end up with an entropy that's of the same order of magnitude as typical progenitors, neutron stars, or whatever your collapsing object is, and much less than the Hawking-Bekenstein entropy. Okay, so what is this thing then? It is a vacuum Schwarzschild exterior, an interior that's de Sitter-like, has no singularity, which is, I think, good compared to what you had in the classical theory. You can think of this vacuum energy as a Casimir-like effect, a bag constant, if you wish, just like in You guys know about the bag model in nuclear physics. So it's like a bag constant, but instead of a gluon condensate, you can think of it as coming from a gravitational condensate. There's no problem with unitarity. There's no Hawking radiation. You don't have any information paradox, no problem of entropy. Stable as far as we could tell in that model by just looking at thermodynamic fluctuations. To really do stability properly, you have to have a Lagrangian and an exact solution. That's what we're doing now. Nothing becomes Planckian pressures or densities. And, okay, they can also think about the interior.
Does it mean
What?
you avoid completely very large densities? And can you generate cosmic microwave background radiation?
Oh, wonderful. Okay, that's a whole other topic. I'm happy to talk to you after. But yeah, you could think about the interior from a cosmological point of view by scaling it all the way up. But for the moment, let's stick to black hole physics and stellar-like scales, or at most supermassive black holes. But did you have another question? You said some. No. Okay. Yeah, let's come back if you want. If you want, we can talk about that. So let's now try to get to astrophysics. Okay. So there's a lot of work still to do on the microphysics, but I think we've progressed quite a bit from this very simple model we had 10 years ago. And now I have the Lagrangian. There's a set of equations to solve. We can actually, I hope, have a solution very shortly. And with that, we'll be able to do all the stability analysis, all the fluctuations, everything of the microphysics will be under control. And then the question will be, can we see this thing? Is there any chance of telling whether this idea is right? So let's go now to what it might look like. Well, first of all, it's going to be cold and dark and compact. If it's really on this kind of scale, then anything's happening. On most astrophysical properties, orbits, accretion is all going to be essentially the same. You're not going to be able to tell it's a black hole or a gravastar. But the matter doesn't completely disappear down this hole. There's some kind of surface layer which can respond, ring, if you wish, when struck, like a bell. That's important because it could lead to gravitational wave signatures, and there are normal modes associated with this surface. So spectacularly, this could lead to discrete spectra of gravitational modes, gravitational waves, just like the difference between a classical atom in which something spirals down and falls in, and the Bohr atom, where you have energy levels and discrete spectra. So this is our challenge, of course, to calculate the spectrum, but you can already see qualitatively that if you have a bubble basically with discrete normal modes, it's going to radiate at those discrete frequencies. I think there's no problem from this anomaly effective theory, coupling to standard model baryons and electromagnetism, that this thing will support electric currents, and therefore astrophysically could be quite different than black holes, because rather than obeying this no-hair theorem where everything collapses in, there can be a magnetic current. There can be magnetic fields and current sheets, perhaps, in this surface. So this, I speculate, of course, I can't do the calculations yet, but this could be quite different, a more efficient central engine. People ask always about formation. Well, the formation is certainly going to be a very violent event, a phase transition in which gravitational energy is essentially converted with near unit efficiency. And you get rid of a lot of baryons and leptons, and convert them into leptons and entropy. So this, again, is beyond our ability to do a calculation yet, but certainly it's going to be a very dramatic and violent event. The other interesting thing is, I showed you only the non-rotating case, but once you do rotation, then you see basically from the point of view of Birkhoff's theorem, if there's nothing outside, then it has to be Schwarzschild when it's not rotating. When it is rotating, you don't have that theorem, and therefore, if you have a rotating condensate, the rotating condensate could have an exterior geometry which is distinguishable from Kerr, and doesn't obey the no-hair theorems. So that's where I've put some of the focus recently. I've been thinking about whether or not we could see this thing in VLBI submillimeter VLBI, looking at the event horizon, say the largest object that we can probably look at is the object in our center of our galaxy, Sag star, and this shows from these guys' work just targets for VLBI imaging of galactic supermassive black holes. I think stellar mass black holes are going to be too hard, too small to see anything. We don't have the angular resolution, but we just might be able, with 1 millimeter wavelengths and essentially aperture synthesis on the size of the Earth's diameter, we might just be able to see what's going on in the center of our galaxy and maybe Andromeda and a couple of other nearby galaxies. So that looks to me to be the best hope for the short term, medium term. Been also thinking, I'm going to end here soon. I just want to tell you what I'm thinking about and really want to hear your reactions about other possibilities for detection of, for some sort of way of determining what's going on at the event horizon or would-be event horizon of black hole candidates. The other thing one can think about is can we see something in the accretion models in which the X-ray continuum thermal spectrum determines the ISCO, innermost stable circular orbit, and particularly if the Kerr geometry is modified, those orbits could be modified, and that's an important calculation we need to do in order to see if there's any way that data could be sensitive to that. So various people, this is a small industry I guess now, people like Saltis and Johansson have been looking at testing the Kerr solution. If there are violations of no-hair theorem, either from our picture or others have been suggested, this shows from papers of theirs what might be the dependence of the innermost stable circular orbit if you have deviations from the Kerr quadrupole. The Kerr quadrupole moment is fixed in terms of the angular momentum parameter, but if they just consider an arbitrary deformation from that by epsilon, and they ask what happens to the orbits and what happens to the ISCO if you do that, and basically try to argue that this might be detectable in near future through X-rays. I think the best thing is going to be the smoking gun here is going to be in gravitational radiation. I already mentioned that there's this spectacular prediction that there would be discrete-like lines. So this is really, I think, without getting into some of the details of what's happening with accretion and matter falling on, I think the gravitational radiation is going to be the most clean signal if we can ever get it, and maybe even by looking at pulsar timing. The other thing I want to mention is this phi field. We'll have a paper out with Valen soon that we've looked at this field propagating, and actually it does predict scalar breathing modes in the gravitational waves. I think the amplitude is going to be too small as far as our estimates go from sources, but in principle this is a whole new effect that isn't there in Einstein's theory, namely scalar in addition to spin 2 transverse trace-free modes. And I'm sorry I can't give you a prediction for this meeting, but I really would love to hear you guys' reaction. If there's any way of testing these ideas of a surface in a would-be black hole candidate in merger events. Probably not in electromagnetism, although I don't know, but in gravitational waves. Is there a way can we develop something like a smoking gun signature which would really rule out this theory or provide evidence for it?
So for classical black holes, we know what the polynomial modes are.
Right.
And if we can measure more than one mode, we can determine its mass and spin angular momentum, and that determines all the modes. And in this case, what should we be looking at? Are the polynomial modes, so-called polynomial
Yeah,
modes,
I mean, so well, they
extra hair?
yeah, that's right. So first thing to say is the exterior perturbations, you know, just following, say, Schrödinger-Szekeres are going to be the same. However, if there's no hair, let's assume that first. But then the boundary conditions are quite different. So instead of having these imaginary parts and the ring downs in the quasi-normal mode spectrum, I would expect you know, to have emissions at those frequencies, which without that characteristic decay, time damping. Okay, and that what exactly happens depends basically on the boundary condition of how the gravitational waves are coupled to the surface.
Yeah, some of
Do I
us
put
have
Dirichlet? Do I
yeah.
put Neumann? I mean, that's what I've been sort of struggling with.
We are also worried about, you know, things like naked singularities. Can we look for naked singularities? They too, the boundary condition is different and might affect what we look for. And this is another scenario where, you know, what we expect for the final merger phase might be different.
Mm-hmm.
So it would be good to know what kind of signatures we should be looking for.
Right.
In principle, we can do it if there is, if there are massive, I say massive, but something like 50 solar mass black holes. We can observe the ring down signals for classical black holes right in the heart of the detector. And so it could be really a smoking gun evidence for classical black holes. But if we don't see it,
Suppose if you don't see the ring down, for example, the question will be, what are the ambiguities? Could it be interpreted in different ways? Of course, our challenge is to give you a prediction that's hard and that, you know, we live or die by. But yeah, the thing I'm worried about, and maybe you can help me understand, is if you don't see that, what you're expecting, how many different, you know, possibilities are there? Is this smoking gun for what?
no, I don't. For binary black holes of stellar mass,
Yeah.
up to hundreds of masses, they are supposed to be very clean systems. There is no environment, there is no contamination, and they are completely dictated, we believe, by general relativity.
Mm-hmm.
If that's the case, and if they are black holes, then we must see them. If they are not, then we will be,
Okay.
you know, we won't immediately jump to
Yeah. Right.
conclusion saying, oh, they are not black holes, but
Right. But you're saying surface modes or different boundary conditions would show up pretty quickly.
anywhere between 80 solar mass to about 150, 200 solar mass. That's the very sensitive part for quasi-normal modes in advanced gravitational wave detectors.
So
Okay.
do you have a prediction for the spectrum of the surface modes? You know, is this spectrum different from the quasi-normal modes that is?
No, as I was answering, I haven't done a detailed calculation yet, and there's a lot to do. But my expectation would be that you would get the same kind of quasi-normal modes at those same, but the damping will be different because the damping depends on assuming that everything falls in. Okay, it's basically you're basically putting an infalling boundary condition on the modes in the standard approach.
That's not
And-
free. I mean, in Einstein theory, they're all, once you determine two or one mode, you
Yeah.
determine frequency and damping time. Everything else is
So it depends on the boundary condition, and it depends on this no hair thing, which I'm looking at also carefully. But in the first approximation, it seems reasonable to think the hair would be small. So these epsilon it may be very hard to determine it, you know, just because you have these kinds of small parameters floating around, you know, which is the thinness of the surface. So the hair could be there, but I'm not going to bank on that. I think the better signature is the damping rate of the quasi-normal modes being different, because if you have a surface, it's not the boundary condition is definitely going to be different.
I think what we discussed privately, the accommodated signatures of black holes that we see tells you that your surface must be absorbing.
Mm-hmm.
And from this point of view, because if the surface was not absorbing, then everything which hits the surface will radiate its rest mass as some thermal emission.
Yeah, I mean that's
And you will
we've
get,
been discussing it.
And you will get for every accreting source, you will have a thermal component which will be stronger than the disk or whatever
Yeah,
component
so-
comes from. So the only way to avoid it is to have the pure surfaces should be absorbing, and from this point of view, they will behave effectively for the outside observer like a black hole. The interior will be different, but for
Electromagnetically.
but for this you have to jump into the black hole to see that the interior.
But the gravitational waves, you agree, would be different.
Okay, but now, why, if it is absorbing for electromagnetic waves, why it is not also absorbing in the same way for gravitational waves? Then you have to
They're quite
to
different.
come out with a very peculiar system in order that this will be different from standard black holes for the outside observer. Because what I'm saying, what I think is that already from present astrophysics, we know that if these objects exist instead of black holes, their surfaces should be absorbing.
I agree. To some extent. I mean, it's a quantitative question, right? So what we have been discussing is there was some papers by Narayan criticizing these ideas and saying that they're ruled out because if you just look at accretion rates and assume that that accretion is turned into thermal energy, then you can look at the black hole candidates and say there's no such thermal energy coming out in the near infrared, so there can't be a surface. But of course that depends on A, the surface re-radiating, and B, first of all it has to thermalize, and second of all it has to re-radiate. And so I agree that we have to explain what happens to ordinary matter in falling onto this surface, and what I don't expect at all to be fully radiating back. But the question is, with what efficiency does it radiate back? And if it's too high, then it will show up. If it's not, if it's smaller than like 1 part in 1,000, it's immediately invisible. It looks just like a black hole. But I agree, it's an issue we have to think about.
You said there might be some scalar radiation associated with this
Yeah.
field. Now, there are rather tight, fairly tight limits on from the pulsar timing, the spiraling in of the orbits.
Yeah, looking at that now, actually.
The amount of scalar radiation.
Right.
So
Basically, this thing is very, very weakly coupled because its source is the curvature invariance. It's like r squared. So although in principle it's there and it's a very interesting effect, our first estimates, which I'm trying to do a better job now, but our first estimates are that it's greatly suppressed. So basically you don't produce enough amplitude to see in LIGO or to affect the Hertz-Taylor pulsar. Can't radiate enough energy away because it's too weakly coupled. So these fields are there, but they don't do much in most of the, so for example, sometimes people ask scalar tensor theories like Brans-Dicke, completely different than Brans-Dicke. It's coupled only to these higher order curvature invariants through the trace anomaly. So it's totally negligible in the solar system, and all the, you can think of it as good or bad, but it's a prediction that it doesn't interact in the standard ways and therefore evades all those bounds. But the Hertz-Taylor gives one of the most stringent. Chuck?
If you have a hypermassive neutron star with
Yeah.
the baryon density in equation state, can you take me through the transition? What happens to the baryon density?
Yeah.
What happens to your scalar field as a function of time?
Yeah, the honest answer is no, but I can speculate and give you a hand-wavy answer. Okay. So basically, the baryon number will not be conserved in this collapse because the same sort of quantum anomaly effects, which I'm talking about in terms of the corrections to Einstein's theory, also predict that there will be violations of baryon number. That's the chiral anomaly in curved space. And so if you compress all your baryons down to something like the event horizon, when the event horizon, your parent horizon starts forming, at that point there has to be, these forces have to push you back out and in an explosive event in which many baryons are destroyed, most of them. You expel a lot of them, and you presumably leptonize those baryons by violation of baryon number from the anomaly. So that's not.
So
That's the picture I have, at
neutron
least.
star
Yeah.
collapses from a neutron star radius to the Schwarzschild radius. And there's an extra source of energy.
Well, you basically convert the gravitational energy into. You can freely, through these anomaly terms, you can freely convert your rest mass energy into gravitational, into radiation, into an explosive event. Essentially, efficiency 1.
Still, if you think it is an explosive event, that would make a drastic change in the picture, say, of a supernova.
Supernova, yeah.
The formation of a black hole through some sort of
Yes.
process.
Yeah. That's that what you're getting at?
Yes.
I see. All right. Well, great. It's a good question. I can't give you a quantitative answer. I've tried to. I asked people like Chris Fryer's not here, I see, but at Los Alamos, I was asking him what happens to your supernova code. Forget for the moment all the detailed microphysics. I just tell you by hand when something hits the what you think is the horizon, some fraction of it is kicked back out at you. Or, I kill baryon number and just kick out, half of the matter back out at you. What happens? As far as I can tell, that's never been, that question has.
You're not allowed to do this.
Why?
This is exactly what I told you before, the astrophysics or observations of accreting black holes do not allow you to kick out.
No, we're talking about the explosion now. We're not talking about the quiescent object. Yeah, I'm not talking about.
It is still the same process, just happening faster. You have accretion onto a black hole, and you have accretion onto your star or your object.
Yes.
And if the accretion is, you have to find very good reason now, which it should be something very contrived. You say, well, if I accrete slowly, I absorb it. If I accrete very fast, suddenly the surface becomes different and it reflects.
I mean, this thing has to figure out in real time. I mean, if you have already a de Sitter interior, you already have a surface. The physics is different. It's quasi-equilibrium physics. If you're creating this thing for the first time, then there has to be an explosive event in which the interior blows out.
And the first time you create a very tiny thing in the center, this is how black holes form in the collapse. You create a very tiny
So you're going to
in the center.
but it's got to blow.
And you created it on a very small scale, and then it begins to grow by accreting the matter that falls onto it.
No. But the picture of it.
It's not. You don't suddenly take the whole neutron star, convert it to a black hole.
Look. If this works at all, what you've got to have happen is in the center of this object as it's forming, it has to produce this phase transition to a de Sitter phase in which there is now a repulsive term in the energy momentum tensor which blows things out. Okay, that is not something in a standard accretion.
Surrounded by your surface that stop the blowing out.
No. It's the interior which has to blow out before you've even formed a surface. That's a different process. But look, now we're into speculation. So but it seems to me a very different non-equilibrium process.
I have a simple question.
All
What
right.
is the causal structure at R equal to 12?
What is the causal structure? It's just like a neutron star, in which the surface is very deeply redshifted.
It's no longer a null surface.
Right. It's a time-like. This thing is a time-like tube. So it's just a static object, which happens to be collapsed pretty close to its. It's not a black hole.
So the most of the very different, I think, from Schwarzschild.
Great.
So I suggest the following, in the
Yeah.
interest of time, we'll thank Emil now, and then we can continue. With the slides. I think there'll be a lot of. Okay.
Thanks a lot. Yeah. So.
Okay, we have two choices. We can continue discussing, which I think is very interesting right now, and have more questions, or we can take a short break and come back for an extensive discussion of both. How about we have a short discussion relating to this talk, now for the next 5 or 10 minutes, and then have a break and come back for a longer discussion in C520
Sounds fine.
in 10 minutes. Thank you.
Yes, sir.
So, you said you can sustain magnetic fields.
I think so, yeah.
How strong magnetic field
Ah.
can sustain, how long you can sustain?
Wonderful. Okay, so now I need to know about the permittivity, conductivity of the surface, and I don't have that estimate for you. I don't know.
So you basically cannot have too strong or sustain too long, because otherwise these isolated black holes will show up as pulsars, for example. They carry magnetic sphere and spinning, and then we don't see those things.
So you want to say the magnetic field has
Yeah,
to
if you
collapse.
have an isolated black hole and it's
Yeah.
spinning and it carries magnetic fields, then maybe you should have magnetic
Do we know that all the radio pulsars are neutron stars?
Oh, they have surface, they have hot polar trap.
We see thermal radiation from some of them.
You measure the
Isolated pulsars, we just see a radio.
There are a lot more pulsars, right, than you tell me, but there are a lot more pulsars, I think, than
You measure the mass is 1.47 masses. Most of the pulsars.
So you have, I mean, the structure on the surface is a condensate of, space-time fluctuations. It's a condensate of some gravity.
Well, the inside is a
Why do you expect it to have magnetic properties? It's basically neutral with respect to electromagnetism. Why do you expect that surface to have any magnetic permittivity?
Well, okay, good question. I think it's from these anomaly terms. It's coming from it's a skin coupling to ordinary standard model charge fields. So it should behave. It should be.
So there is.
It should be overall neutral, but no reason why it can't carry currents. I don't think.
But
Which is what the spectrum conductivity is.
Right. No, that's the right question.
Which might be not very long.
Okay, no, absolutely right. I mean, so then I have to, do some scattering problem in that surface to determine the mean free path and the conductivity. It's hasn't been done yet.
So I just want to understand
Yeah.
in a different way of thinking
Yeah,
about this
yeah.
problem. So you have at this horizon, you have a mode spectrum that's very soft, and it's actually getting negative for these things that you're calling as the condensate. So there are some excitations on the surface that have a negative spectrum, so they condense. And the reason so there's an attractive interaction that produces a negative mass for those excitations. And now you're saying that the dark energy pressure that's blowing it out keeps it stable.
Yeah.
And typically, if I just give you bosons with attractive interactions, the condensate would have infinite density unless I gave it some
Right.
finite repulsion.
Right.
This repulsion is coming from the dark energy from
Right.
inside.
The gravity is its own trap.
Okay.
It's a condensate in its own trap.
And so there must be a bunch of modes
Yeah.
which are different from the modes that are in a classical theory, because now the surface mode is oscillating, where you have a surface energy density that is changing in response to the dark energy. So that should have a different spectrum than just the classical modes. Right? So there's something about the one Fermi length scale that you have here.
Okay, at some scale I agree, but I would expect the low-lying modes to be essentially the same. I mean, I basically going to look at Chandra-Sekhar's analysis, right? Of the no,
The width of that is 1 Fermi, but the size is.
it's big. Yeah.
So there are modes which care about the width of that.
There are the modes that care about the width, right?
That are
Yeah.
very high frequency.
Yeah.
Right.
That probably are out of your spectrum anyway, so you'll never be able to see it.
Yeah. But most of the modes we're talking about don't care about that, do they? I mean, for them,
The potential,
yeah,
everything is happening at the potential.
right, at the 2m, 3m,
Exactly.
right, so,
Also, I don't think it's correct to think of the interior as somehow supporting the shell. I mean, the shell has to overcome the pressure gradient from zero pressure outside to negative pressure inside. Right?
yes.
So you need a large positive hoop stress in the shell in order to keep the shell from.
You need a tangential stress, yeah, you need an anisotropic stress there, right, yeah. But it's a combination of that, yeah, I mean, it's that's, right, yeah.
And then what that does to the normal motion of the shell is, I think, not obviously at all similar to what you expect from
Because it breaks the symmetry. Okay, it's good questions. Yeah.
So threshold for this phase transition, or from normal matter to this, does it occur at a local energy density? Does it occur at a global Schwarzschild condition?
A Schwarzschild condition.
How does a small piece of matter near the center of this collapsing hyper
That actually answers
massive.
Sweet's question. Does it really grow from the center slowly, or?
Yeah, I mean, we're right.
When does it know that it should?
Yeah, we're right now, we were discussing before, we're right now looking at some simple 2D model and the causal picture you get. So if you try to make a black hole with some incoming shell, just artificially, numerically I want to make a black hole. So I send in a shell of light, okay, with a certain energy density. So it would make a black hole here. You can see that, sorry, it's not the right picture. So it would form a singularity. This would be the classical geometry. And then there is a certain place, right, where the energy density first goes inside its apparent horizon. That is the place where, on the whole surface now, on the whole r equals 2m, but that is the local place where the fields have to know that something fancy is happening, right? So if we look at fluctuations here, these fluctuations just emerging at that point, then they realize that something's wrong. The classical geometry can't continue at that point, and you've got to have the phase transition happening there, essentially.
Shouldn't it be like the trapped surface condition?
Yeah. Before the apparent horizon
But each
can
time
really.
the horizon goes out, you're going to have to do this again and again.
But depending on how non-uniform
Yeah, but it's going to be, this is simple model, right? So it's,
that could happen either in some little core or near the.
Yeah, it could be the size of a galaxy.
Question for
before you
Mark.
figure it out.
But if you're accreting onto
You wanted to ask
an
question.
object that's supposed to be a black hole or whatever this is, then you're going to be increasing the apparent horizon each time you throw a bit of matter into it. And so it should do the same thing each time, like.
I mean, it should
So-
it should grow. It should
But
not.
then if you're saying that this
Why is it
should,
exploding is a question
Yeah.
that people, I think, want
Okay.
to understand.
Why is it
Does it
exploding?
happen locally and slowly grow, this phase transition?
Okay, so this is, okay, so there are different questions going on here. Either are we assuming that you have it already and we're accreting, or are you assuming that ordinary matter is falling and making what would be a black hole? Which, let's discuss one at a time.
Let's talk about your shell.
Yeah,
And the shell just crossed the horizon. Right
yeah,
now.
right.
So
That's when we see the large stresses growing
So the stress is forming on the horizon.
on the horizon.
But what is inside? The light did not reach yet the
They're not
interior.
yet reach inside.
How does the interior know that it has to be converted to Einstein, the cosmological concept has to develop?
Okay. So you want to know causally, does something happen here first or here first? It has to be here, I think.
Yeah, it has to be here, but
Bit-
then you have, do you expect to have
I would expect something to happen.
The zeta phase propagating inwards?
Yeah, I would expect the phase transition to happen here and basically follow the matter. And so if it's not light, but massive matter, it can overcome, it can go faster, right? So I would expect the phase transition to happen here, and here you form de Sitter, which is going to blow out material. But
But,
Yeah.
Well, I mean, another issue is, say you have a classical star, you first form an apparent horizon sort of towards the outer edge of the star, which is a fairly uniform density. Right. So then the question, well, and let's assume that star has quantum information associated with it.
As an entropy, yes.
And a lot of that quantum information is inside where the apparent horizon first tries to form. So, you know, what happens to that quantum information, or can it get out, or is it trapped inside?
I mean, since I don't form a black hole or a horizon at all, I mean, I don't think there's any trouble with entropy. I mean, the information, it's just, I mean, there's a phase transition, something dramatic from the point of view of ordinary physics, but no violation of causality, of entropy, of standard quantum mechanics. It comes out, yeah, it comes out. All this stuff comes out, and it has to blow it off. But what I showed you is that just simple estimates get you about an order of magnitude, within an order of magnitude of the progenitor. So, you know, maybe I blow out 90% of it, but I don't have to get rid of 10 to the 19 or something like that. Sorry, in the static object, or in what context?
In the final object.
In the final object, no. No, it gets very close, but never.
I'm not talking about the event, about the environment.
I think the answer is also no, right? Because the apparent horizon is basically defined by.
But you could have an apparent horizon formed temporarily.
You could have a temporary, yeah, in some.
In this initial.
Sure.
As you're doing phase transition.
Right.
But then you would have to disappear, which
Right.
would require negative energy, but that's.
But I've got that, right? I mean, there's negative energy here, at least in the narrow region.
Well, then maybe it's a bigger region before you sum it up.
Correct. So the final thing does not have an apparent horizon in this picture. Yeah.
Is it possible to construct equivalent scalar tensor model?
It is a scalar tensor model, but with a unfamiliar kinetic term. Okay. So it's not of the standard types that have been discussed by, for example, Cliff Will and others.
What do you mean with non-standard?
I go back and show you the Lagrangian. It has not. It has a fourth order.
Hyperbolic.
I'm sorry.
Hyperbolic.
Hyperbolic. Is that what you said?
The resulting equation for the scalar model is hyperbolic.
Hyperbolic. Yeah.
Then.
But it's fourth order and derivatives.
We can test by using calculation because.
Yeah.
So if you have some.
If I give you equations, we can do it. Yeah. No, but I would love to talk about that. Yes, because that's where I am now. I'm just to the point where I can do this and write the equations, and I think it becomes a well-defined problem. Solve the equations.
You mean well-defined and well-posed?
Well-posed. Yeah. Yeah. It's a well-posed problem. So the first step is to construct from this microscopic Lagrangian the Gravastar model. So something we just assumed was there was this surface, and now by looking at.
You can start from the usual star.
So the simplest thing to do first is just static, right? Simplest thing is to look static, spherically symmetric. Then you want to maybe put some rotation on it, see how that changes. But then.
Some static solution may be disconnected mathematically. There should be some isolated island in the mathematical solution space.
I don't understand.
Some static solution may
Yes.
be dynamically irrelevant in astrophysics.
I don't understand that statement. Why irrelevant?
Because maybe it's an isolated island in some other special solution. There's no way to reach from some.
Oh, okay, all right. Well, okay, well, the first step, I would say, is to find this solution. But then, all the interesting questions, or many of them, come from the dynamics of how I get there. And those are, at the moment, all speculation. Okay, so I start to see some picture from this two-dimensional model, but it's pretty crude still. So I'd love to have some more interest here and see if we can do better. So there are very different directions. I've been concentrating on writing down the equations, getting the model that in a way that I feel is under control, makes sense. I know what the assumptions are, and everything can be controlled. Next, next is to ask all these other questions, and there we, may have to do some phenomenology. We have to, just guess what the right boundary conditions, see if we can't, look at a range of different possibilities and see if we can't predict something for magnetic fields, for gravitational waves, for astrophysics.
Any more questions? Okay. Well, we're already 4:30.
Yeah.
I wonder whether we should reconvene again. If there are people interested in continuing this discussion with Emil, we can try to do that. If there are people who would like to talk also about the morning discussion, we can have it together. So how many people would like to have a general discussion about both talks in a few, maybe in 10 minutes?
Will that be cookies?
There will be cookies.
There will be cookies. That's all that matters, right? Well, we don't care about the talks. Yeah. Okay, I should turn this one. Not fully collapsed.
So for those of you who are interested, why don't we just meet in the small room there, and I'll bring the cookies there, and we'll see how the discussion goes. Okay. Let's thank Emil again.
Thank you.